Hello friends, welcome back to our MOOCs course on the fundamentals of nuclear power generation, and today we are looking to finish our second module on the topic of radioactivity and nuclear reactions. We already had 3 lectures on this particular topic, and if you have gone through all of them carefully, I am sure you have quite decent knowledge about this phenomenon of radioactivity. In first 2 lectures, we discussed mostly about the natural phenomenon or natural radioactivity of certain isotopes, where an isotope can go through spontaneous decay leading to the emission of certain particles and also release of high amount of energy. And in certain situations, the daughter particle or daughter isotope, which is the product of this dissociation or disintegration, itself can be radioactive in nature, leading to the formation of long chains or long radiative chains. So, such kind of natural radioactivity is limited to only certain isotopes. However, in the third lecture, you are introduced to this very interesting topic of artificial radioactivity or induced radioactivity, where any stable isotope can be forced to represent or display radioactive behavior by striking it with a suitably chosen high energy particle. Like we have seen the examples. If we quickly revisit our coverage on lecture 3, in the topic of artificial radioactivity, which was first introduced by the daughter of Marie and Pierre Curie, and that is Juliette Curie with her husband Frederick, or Irene Curie and with her husband Frederick Juliet. So, where they took the very stable isotope of aluminum 27, strike that with high velocity alpha particles, leading to the formation of phosphorus 30, which was found to be radioactive in nature, and that displayed continuous emission of beta positive particles or positrons. So, this way, the way they showed, similarly lots of other researchers works on that, and now it is a proven phenomena that any stable isotope can be converted to a radioisotope by striking it with a suitably chosen particle. While the choice of particle can be alpha particle, can be electrons, which is the beta particle, or something else, neutron is generally the most favored one. The reasons we have already discussed, neutron being electrically neutral, it does not face any kind of electrostatic repulsion force from the nucleus, and therefore, it can easily approach the nucleus, which is not possible for proton or alpha particles. It also has a mass of about 1 mu, which is sufficient to cause some kind of damage to a nucleus if it has high amount of velocity. However, the nature of the interaction a neutron is going to have with a nucleus depends on 2 factors primarily. One of them is the energy level of the neutron, the kinetic energy, that is we have classified the neutrons depending upon their velocity level or energy level into several categories, but out of that primarily 3 terms are very commonly used: slow neutron, intermediate neutron and fast neutron. Fast neutron generally refers to neutrons having energy greater than 1 MeV, whereas slow neutron term is mostly reserved for neutrons having low energy less than 1 electron volt, or in certain situations 10 electron volt. Intermediate is something in between. But there is also the concept of thermal neutron, which refers to a neutron which attains thermal equilibrium with its surrounding, and accordingly it is having the lowest possible energy level depending upon the temperature of the surrounding. Corresponding to 20 degree Celsius, the energy corresponding to a thermal neutron is 0.025 electron volt and a velocity of about 2200 meter per second, which are the common values that we associate with thermal neutrons. Thermal neutrons have certain interesting properties which we shall be discussing later on. But for thermal neutrons, the values that I just mentioned, they can be calculated by equating its kinetic energy, which is half mn Vn square, to the thermal distribution, that is k into T, where k is a Boltzmann constant. Accordingly, we got that value for 20 degree Celsius, this energy is found to be 0.025 electron volt. And the other important factor which governs the nature of neutron nucleus interaction is the nuclear cross section. Cross section is a concept which relates to the probability of having a certain interaction happening when a neutron of certain energy strikes a nucleus. The rate of such interaction has been found to be proportional to the neutron flux, which is this I. It is also found to be proportional to the density, nuclear density or number of nucleus per unit volume of the target material, and also it has been found to be proportional to the volume of this. So, N A into x, this 3 terms together represent the total number of nucleus present in the target, and I is the characteristics of the neutron beam that is coming to hit this target. But the constant of proportionality is this sigma, which we have defined as the nuclear cross section. It can be visualized as the amount of area that a nucleus projects or presents to a beam of neutron to cause any particular kind of interaction. We have seen there are several possible interactions, and I am producing this particular figure which we discussed earlier. Commonly we can have 3 types of interaction. One is, first is scattering, where the neutron and nucleus interacts with each other, exchanges some energy and momentum, and then go to different directions. Scattering can also be of 2 types, elastic and inelastic. Elastic scattering refers to a billiard ball or carom coin types of collision, where they come from different directions, and there is a perfect conservation of both momentum and kinetic energy. Just think about what happens in a carom board. Like if we strike a stationary coin with the striker, then a part of the momentum and energy carried by the striker is transferred to the coin, and then accordingly both of them choose certain directions and velocity to move on. That is exactly what happens in an elastic collision. The inelastic collision refers to much higher velocity level neutrons. In case of inelastic collision, there is a perfect conservation of momentum, but kinetic energy is not conserved because a part of the kinetic energy is transferred to certain photons, generally gamma photons. Corresponding collision cross sections are represented as sigma E for elastic scattering and sigma I for inelastic scattering. Quite often they are combined together into one common term, sigma S, which represents the summation of sigma E and sigma I. The second kind of interaction that is possible is the absorption, when the neutron is able to penetrate inside the nucleus, and after penetration there can be 2 types of possibilities. One, where the neutron remains inside the nucleus forming another isotope of the parent, which is capture or radiative capture. Other is the neutron enforces enough amount of energy or imparts enough amount of energy to the nucleus, so that it gets split into 2 components, 2 daughter nucleus, which is fission. So, both radiative capture and fission are of absorption type. Sigma C and sigma F are the corresponding cross sections, and quite often we use sigma A to represent the absorption cross section, which is nothing but the summation of sigma C plus sigma F. And there is a third kind of interaction which is much rarer compared to the previous 2, which is transfer. That is, when a neutron strikes a nucleus, it leads to the emission of some more neutrons or certain particles like alpha particles or protons, etc. While this third kind of interaction is mostly associated when certain heavier particles like alpha particles strikes the nucleus, but occasionally it is also can be associated with the neutron collisions. So, all these 5 types of interactions are possible when we have a neutron nucleus interaction, and corresponding to each of them there is a certain probability, or you can say one nucleus presents certain amount of area to the neutrons to have each of this kind of interactions. So, the total cross section a neutron can have, or I should say a nucleus can offer to a particular neutron, is just a summation of all this. So, total sigma can be a summation of sigma E plus sigma I, these 2 corresponding to the scattering part, plus capture plus fission corresponding to the absorption part, plus just transfer part, which may be relevant in certain situations, but mostly it is negligible. So, this is the total cross section a nucleus can offer to a particular neutron of a particular energy level, and hence if our interest is to identify exactly what is the probability of say fission occurring, I must mention, which I have already done earlier also, the value of each of this cross section for a given nucleus depends upon the velocity level of the neutron itself. Now, if I provide a certain nucleus and a neutron of a certain velocity, then all these 5 numbers are given. So, we know all these cross sections. Now, if we want to know exactly what is the probability of fission occurring, then that should be the fission cross section divided by the total cross section that is available to this particular neutron nucleus pair. So, this is the probability of fission that can occur in that particular situation, and this way we can identify the probability of all other kinds of interactions as well. So, with these concepts of artificial radioactivity, today we shall be checking about the conservation of energy and momentum, and then we shall be solving some numerical problems to give you some more idea about how to tackle this kind of situations. But before that, a particular concept I have to mention, which I could have done during the first module itself, but still thought about putting it better here, the concept of a rest mass. While in common physics point of view, we keep mass and energy as 2 separate entities, but following Einstein's theory of special relativity, both are interchangeable, that is mass can be converted to energy and energy can also be converted to mass, and hence the special theory of relativity says that, or theory of special relativity says that the mass of a body is not constant, rather it keeps on changing with the velocity. But when the velocity of the particle or body is 0, then corresponding mass is called the rest mass, which is commonly denoted by m dot or m 0. All the values of mass for proton, electron, neutron, whatever we are discussing so far, or the mass of any particular nucleus, all of these are actually this rest mass. That means, rest mass for a proton, if someone asks you, you have to say that that is 1.007825 AMU, because those are the values that we have already mentioned, those are all for rest mass. But when the particle is moving with a certain velocity, then corresponding mass can be given by this relation, no proof required for this, but can directly take it as m equal to m naught divided by root over 1 minus v by c whole square, c being the velocity of light in vacuum, that is 2.9979 10 to the power 8 meter per second. Now, you can clearly see c being such a very large number, we need to have quite large value of this v to have any contribution on the value of m. If the v is small compared to c, then the denominator basically reduces to 1 and m remains quite similar to m naught. But this particular relation is important only when the velocity is a good portion of this c, that is this v needs to be a good 10-20% of this c, then only the value of m will be substantially different from the rest mass value. Otherwise, there is no point considering this concept of change in velocity with kinetic energy, we can always operate with the rest mass. But another thing we can learn from here, if v becomes greater than c, then what happens? Then the denominator becomes imaginary, which is definitely not possible, which signifies that no material object can have velocity greater than v. The largest it can have is equal to the velocity of the light. In that case also its mass becomes infinite. But energy, accordingly we can define 3 different energies for a particle. The energy corresponding to this rest mass is called the rest energy. That is, if the value of this rest mass m naught is completely converted to energy, then the amount of energy that we are going to get, that is equal to this rest energy. Similarly, when a particle is moving, its mass is expected to be different from the rest mass, and hence its energy level also will be different from the rest energy. So, this rest energy is just m naught c square, that is, if rest mass is completely converted to energy, this is the amount of energy we are going to get, and that is what we are calling as rest energy. But when it is moving, then total energy is of course m into c square, that is all. Then what is the difference between the two? The difference has to be the velocity with which it is moving. So, that is what we term as the kinetic energy, which is the difference between the total energy and the rest energy, or can be represented as m minus m naught into c square. So, in a gist, whenever a particle is stationary, we can continue to use the rest mass and with rest energy, but whenever a particle is moving, then the velocity of the particle will have some kind of contribution to its energy level, and we must encounter that in calculations related to nuclear energy in particular, where we have conversion of mass to energy or energy to mass. Now, let us take a simple or a very typical nuclear reaction, where P and Q are the reactants, R and S are the product, and also gamma photon can be found on the right hand side as a product. Then there are three different conservations or balance that we have to ensure. First is the conservation of charge, that is total charge on the left hand side must be equal to the total number of charge on the right hand side, or as per the equation shown here, Z p plus Z q is the total number of charge present on the left hand side. So, that should be equal to Z r plus Z s. Gamma definitely does not have any charge, because that is a photon, or you can also visualize that as an electromagnetic wave. Second balance is for the number of nucleons. Total number of nucleons also must be balanced. The parent nucleus presents here P and Q, that is the reactants, they can exchange their charge and nucleons to form the products, but total number of charge and total number of nucleons must be conserved. So, summation of A on the left hand side should be equal to summation of A on the right hand side, or as per the given equation A p plus A q should be equal to A r plus A s. Third, the most important one, mass energy conservation. While in typical thermodynamics or heat transfer, we are bothered about conservation of mass and conservation of energy separately, because there we neglect any kind of conversion of mass to energy or energy to mass, but we can't do that while we are dealing with nuclear reactions, because here there is significant portion of mass can get converted to energy, or I should say a small amount of energy can conversion to mass can lead to huge amount of energy generation. So, mass and energy should be considered together, and hence we have to see this conservation equation as mass energy together. So, that is the summation of mass plus kinetic energy of the reactant should be equal to mass plus kinetic energy of the products. Here one important thing, we shall be seeing examples later on. Here generally we use some kind of unit for mass and some other kind of unit for this kinetic energy, but when we are doing this balance we have to stick to one particular unit, that is either the kinetic energy need to be represented in terms of mass unit, or the mass needs to be represented in terms of the energy units. Let us take one example. We have taken example of a very simple equation, where the proton or common hydrogen nucleus is being struck by a neutron and leading to the production of deuterium and gamma energies. So, first we have to conserve the charge. How many charge we have on the left hand side? That is just 1, because neutron does not have any charge. So, what about the right hand side? Again there is total just 1 number of charge, because gamma is neutral again. So, conservation of charge, we have plus 1 amount of charge on both sides. So, charge is conserved. Now, how many number of nucleons we have? Let us check out the number of nucleons. On the left hand side we have one contributed by this the proton or the hydrogen nucleus, and one contributed by this neutron. So, total we have 2 nucleons on the left hand side, and on the right hand side again we have 2 nucleons here related to this deuterium. So, the total number of nucleons that is also conserved, which is 2 in this situation. Now, come to this mass energy conservation. So, I am directly writing the values of mass in AMU here, but the mass values you need to take from some kind of table or data book. So, total mass of this hydrogen is 1.007825, this one. Mass of neutron is 1.008665, these are standard, and actually I would suggest you try to remember the mass values of proton and neutron, because that will be repeatedly used in different parts of this course. The third one, of course, I do not want you to remember, or I do not expect you to remember, which is for deuterium. It is provided from some data source which is equal to 2.014102 AMU. And last is the kinetic energy. Gamma photon is massless, so its rest mass is 0. Therefore, we do not need to write the mass for that, but Ek represents the total kinetic energy available with the products here. Here one assumption that we have taken is that both the new reactants are stationary. If the reactants are also moving, then there should have been a kinetic energy term added here as well. because then the left hand side also is having some kinetic energy contribution. But important thing is that here this energy terms that we are adding, like only one in the left hand side in this equation, but possibly can be something on the right hand side as well. That one energy term, this E k, that also needs to be represented in the same unit in terms of which we have represented the mass. That means, it has to be in terms of AMU. So, by changing the sides of these terms, we are getting E k is equivalent to 0.002388 AMU, and we have earlier seen from module 1, that is 1 AMU is equivalent to 931 MeV of energy. That is also again coming from this theory of special relativity. So, this amount of mass, that is 0.002388 AMU, if we multiply that with 931, then we can see that the corresponding amount of kinetic energy associated with the products is 2.223 MeV. So, while we have done the entire calculation in terms of AMU, we can finally convert the output in terms of energy or mass, whichever is convenient to us. So, this total amount of energy 2.223 MeV, that will be shared by both the products, that is the gamma ray photons and also the deuterium. But you have to remember that deuterium is having some amount of rest mass, whereas the gamma photon is not having any kind of rest mass. Let us take another example. Here we are having lithium 7 isotope being struck by a proton. So, that undergoes alpha decay to produce 2 helium isotopes. Mass for all the 3 are given, here no gamma photon involved. So, we are having only 3 isotopes or 4 isotopes rather, all are having certain amount of rest mass. And another consideration here, we are considering the problem as lithium isotope to be stationary, the target, and the proton is approaching this lithium isotope with a kinetic energy of 2 MeV. So, let us write the same equation again. Mass energy conservation can be written as, here the mass plus kinetic energy of the reactants should be equal to mass plus kinetic energy of the product. So, we can choose, again I repeat, we can choose either mass unit or energy unit. Let us stick with mass unit here. So, on the left hand side, total mass corresponds to the mass of lithium 7.016004 plus mass of proton 1.007825, plus we have the kinetic energy of 2 MeV, but we can't write 2 MeV directly here, because we need to convert its units to AMU. So, 2 by 931 is the mass equivalent of this kinetic energy, that should be equal to the mass of the 2 helium isotopes plus the kinetic energy carried by these 2 helium isotopes, all represented in terms of the mass unit, which is AMU. So, by doing the calculation, we can find that corresponding amount of kinetic energy of the product is equivalent to 0.020771 AMU, which is actually 19.3 MeV. So, this way we can perform a mass energy balance combined, either using in terms of mass or in terms of energy. Generally, it is convenient to use in terms of mass, because all the isotopes that is involved in a reaction, most of them will be having some kind of rest mass, and so it is generally convenient to do in terms of mass, but you can also do all this calculation in terms of energies. Like this particular situation, if you want to do in terms of energy, then what we need to do? The rest mass, then you have to write the total energy equivalent for the reactant should be equal to total energy equivalent for the product. In that case, the rest mass for both the reactant lithium and proton, this thing should be converted to mass. That means, you need to multiply this with 931. So, once you multiply this with 931, that gives you corresponding energy equivalent. Then we do not need to write this, just 2 MeV directly you can write. And similarly, on the right hand side, this is the rest mass of the product, and you need to multiply this with 931 to get the energy equivalent, and E k can stay in terms of its energy unit. In that case, everything is represented in mega electron volt. So, the answer should remain the same. You should get this particular number directly. So, we can do such mass energy equivalent calculation either in terms of mass or in terms of energy. Also the concept of binding energy that we have identified earlier, or mass defect, you can clearly see in this particular example the mass of the product is 0.020771 mu less than the reactants, and therefore, this amount of mass is getting converted to energy. Now, one important point is we know the total amount of kinetic energy available with the products, which is 2 helium isotopes in this case. This 19.3 MeV will be carried by both the helium isotopes, but how can we say how much will be carried by both? In this case, both the isotopes are having equal amount of mass. So, it is expected that this 19.338 MeV amount of energy will be equally shared by both. But if the product are not of same mass, like you think about the example in the previous slide, where we had deuterium and gamma photon as the two products, where deuterium is having certain amount of rest mass, gamma photon is having a rest mass of 0. So, the energy contribution or energy share for both of them should not be the same, they will be different. But this mass energy equivalence or mass energy conservation does not give you the share about both of them, rather we have to go to the conservation of momentum, that is the fourth criterion that is coming into the frame. In order to calculate, while we can calculate the total energy available with the product just from mass energy equivalence or mass energy conservation, to get their individual share, we are now going to the conservation of momentum, which conservation of linear momentum we can straightway write as a summation of mass into velocity, that is the linear momentum of the reactants should be equal to the linear momentum of the products. Let us take the first example which we have discussed. Here we have deuterium and gamma photon on the right hand side. So, both the product as both the reactants are assumed to be stationary, then what is the total momentum associated with this left hand side? The left hand side total momentum has to be 0, because both of them stationary, or both these reactants are having initial velocity of 0. So, the right hand side momentum also has to be equal to 0, which means the momentum being a vector quantity, both the products, that is deuterium and gamma or photon, should be having equal magnitude of momentum, but exactly opposite in direction. So, that the net momentum of the product remains to be 0. Accordingly, we can write the momentum for the deuterium, magnitude of the momentum should be equal to the magnitude for the gamma photon, but gamma photon is something that does not have any kind of rest mass. So, we can always equate this momentum of this to the energy, where like if E gamma is the amount of energy carried by gamma photon, then that can be represented as E m gamma in c square, where m gamma is the effective mass, effective rest mass of a gamma photon, which is practically 0. I should not say rest mass, actually I am sorry, where m gamma represents the effective mass of gamma photon because of its velocity, and being a photon it will move with the velocity of light. So, E gamma is m gamma into c square, and hence if we divide this E gamma with c, then that should be equal to the momentum of this gamma photon, which is exactly that is written here. Now, to know the value of or to solve this particular equation, while we know the velocity of this gamma photon, you need to know either the energy share of this gamma photon or its momentum. We need to have some information about any one of them, then we can calculate the other quantity, and accordingly we can calculate the velocity of the deuterium, because this is the once we know the momentum of this gamma photon, this magnitude of this one also we know, and this should be the mass of this deuterium into c square. So, we know the mass of that, and this mass from this particular, once we know the effective mass of this gamma photon, actually this P gamma is equal to m into c, which gives you the value of c. Once you know this effective I am doing a mistake here, sorry, I am going back. So, once we know the magnitude of this momentum carried by this deuterium, then we know the value of m into c, m referring to the mass of the deuterium. So, as we know the value of c, we now can calculate the effective mass of this deuterium nucleus, and the rest mass of this one is already known. So, the difference of this these two, or the difference m minus m naught, multiplied by c square is equal to the kinetic energy of the deuterium nucleus, which will give you the velocity of the deuterium. So, this way by combining this momentum conservation of linear momentum with the mass energy conservation, we can get complete idea about the energy share of all the products of a nuclear reaction, and also complete idea about the exact nature of their velocities. Just if we take a very simple example, say we have a reaction which involves two products x and y, where x and y both or any one of them can be a particle and another can be a gamma photon kind of situation, then we need to use both conservation of mass energy and conservation of momentum. That is, the total kinetic energy will be equal to half m a v a square. Actually, here I should not use x and y, I am actually talking about a and b as the two products, then half m a v a square plus half m b v b square should be equal to the total kinetic energy, whereas p a plus p b should be equal to the total momentum for the left hand side. This being a vector addition, I am using these arrows also. So, in a nutshell, there are 4 equations or 4 conservations that we must ensure while dealing with any kind of nuclear reaction. Number 1 is a conservation of total number of charge. Number 2, conservation of total number of nucleons, which will be allow you to describe the equation completely. Then you have the conservation of mass and energy together, and number 4 you have the conservation of linear momentum. This third and fourth together will allow you to get the complete idea about energy and velocity distribution of the products. And by combining all these 4, we can solve any kind of problems involving radioactivity and nuclear reactions in general. So, now let us quickly peep into a few numerical examples. Okay, before that, I finally would like to summarize. We have a very about the energy that we can get from a nuclear reaction. We have a very general reaction as A plus B producing C plus D, where C and D any one of them can be particle and or can be photons. Then mass energy conservation says that mass plus kinetic energy of the reactants should be equal to the same for the products. So, accordingly we can write in terms of either energy unit or mass unit. Here we are writing in terms of energy unit, because we have earlier done in terms of mass unit. Writing in terms of energy unit, we have the kinetic energy of A plus the rest energy of A. This is the total energy contribution from A. Similarly, this is the total energy contribution from B, kinetic energy plus rest energy. That should be equal to total energy contribution from C and total energy associated with the D. If we rearrange the terms, then we can take all the energy terms on the left hand side and rest energy related terms on the right hand side, and then we get Q, which represents the difference between kinetic energy of the products and kinetic energy of the reactants. Here Q is the total kinetic energy of the products C and D in this case minus total kinetic energy of the reactants A and B here, should be equal to the difference between their rest masses multiplied by C square. That is, the net kinetic energy gained by the products is equal to the difference between the kinetic energy of the reactants and kinetic energy of the products multiplied by C square. If Q is a positive quantity, then that represents an exothermic reaction. That is, the products will be having more energy compared to the reactants. So, this is an exothermic reaction and mass is getting converted to energy. However, if Q is negative, that represents the mass of the product is more compared to the reactants. That means, it is an endothermic reaction and energy has been converted to mass. So, the mass energy conservation, which we earlier attained from mass unit point of view, this way we can also attain from energy unit point of view. So, let us go to some numerical examples. Our first example corresponds to the radium isotopes. Just read the problem. We have radium 226 isotope, which is having a half life of 1599 years, and the mass of one nucleus is given. You have to calculate the decay constant and the initial activity of 1 gram of the sample. I shall be coming back to the C part afterwards. Now, we know that the decay constant and half life have an inverse relationship, and a very straightforward one, lambda is equal to log 2 by Th. You need to be very careful about the unit of Th. In this case, half life is represented in terms of years. So, if you are going to solve it, then your numerator is straightforward, that is log 2, but in the denominator you have Th given in terms of years. It is always better to convert that to SI unit, that is in second. Then what we can write in the denominator? We have 1599 years, and in each year we have 365 days. You can neglect the leap year concept, and in each day we have 24 hours, and in each hour we have 3600 seconds. So, the denominator, that is the half life, has been converted to seconds, and if you put the numbers into calculators, you will be getting this. The total value of the decay constant is coming to be something of the order of 10 to the minus 11 second inverse. Please take a note of this unit of this decay constant, it is just inverse of half life. So, it has to be time inverse. Then how to calculate the initial activity? I hope you remember the definition of activity. Activity is defined as the rate of decay, that is minus dN dt. So, initial activity means at any particular time t equal to 0, the rate of decay, that is minus dN dt at t equal to 0, which can be equated to lambda into n naught, n naught being the number of nucleus. So, lambda value you have just calculated. How to get n naught? N naught, we know from that, from Avogadro's hypothesis, that 1 kilomole of any particular isotope will always have 6.0221 into 10 to the 26 number of molecules inside that. That means, here in this case the molecular weight of radium is given, radium 226 as 226.0254. That means, 226.0254 kg of radium 226 will comprise of 6.0221 into 10 to the 26 number of molecules, and from there we are getting the total number of initial isotopes present in the initial sample, multiplying that with lambda, we are getting the initial activity, and it is coming to be 3.6629 into 10 to the 10 disintegrations per second. Now, I hope you remember the units of radioactivity which we have discussed earlier in the very first lecture. So, 1 disintegration per second is equal to 1 becquerel, which is the SI unit of radioactivity. So, you can represent this disintegration per second with becquerel, and finally, the classical unit of radioactivity is Curie, which is the old unit defined by Marie Curie. What is the relation between becquerel and Curie? Do you remember? 1 Curie was equal to 3.7 into 10 to the power 10 becquerel. So, dividing this with by 3.7 into 10 to the power 10, we are getting it to be approximately 0.99 Curie. Does this number 0.99, that is almost 1 Curie, does it strike something? Why you are getting 1 Curie as the activity of radium 226? Because that is how the Curie was defined. The definition of Curie was the activity level of radium 226. So, the answer to this problem is expected to be something very close to 1 Curie, and that is what we are getting. Now, let us go to the part C of this particular problem. It is mentioned that radium 226 undergoes beta decay to produce a nucleus which is having an atomic mass of 227 AMU, and we have to calculate the total amount of energy released during the reaction. That means, the concept of mass energy conservation that we have just learned, that we have to use here. But before that, we have to write the equation. We know that radium 226 is undergoing beta decay. Then what will be the product? Let us try to write the equation first. It is a radium that is undergoing beta decay. So, there has to be electron on the right hand side and antineutrino, which we also have learned in the second lecture. But what about the daughter isotope? What we expect to be daughter isotope? So, we must use the other two conservations that we have learned, the conservation of charge and the conservation of total number of nucleons. How many charge we have available on the left hand side? On the left hand side, we have 88 as the total number of charge. On the right hand side, we have electron having minus 1 unit of charge. Then whatever daughter you are going to have, that should be having 88 plus 1, that is equal to 89 as the total number of charge. So, 89 charge, if you go to the periodic table, that refers to actinium. So, the daughter that we are going to get, that is going to have 89 as number of charge, and from the periodic table, that is actinium, which is having 89 number of charge. Then total number of nucleons, we are having 228 as the total number of neutrons on the left hand side, and how many on the right hand side? Nothing coming from the electron and antineutrino. So, this one should also have 228 as the total number of electron. Actually, one mistake that I have made while doing this, here we are talking about radium 226. So, this number should be 226, and here also the actinium product, that is 89 AC 226 that we are referring to. So, it is not 220, it should be 226. So, we are having actinium 226 as the product, which is having 89 protons and 226 number of nucleons in the product. So, we have to write the mass energy conservation now. Writing the, let us first calculate the total mass defect here. Let us go by the mass route. We can take either energy point of view or mass point of view. We are taking the mass point of view. So, total mass defect here, the mass of the product minus the mass of the reactants. So, rest mass of actinium is already given as 227 AMU, and rest mass of beta, which is electron, that we already know, that is to be 5.486 into 10 minus 4 AMU, and neutrino or antineutrino is massless, mass of radium is given. So, accordingly get the total mass defect to be 0.9751 AMU, and corresponding amount of energy is delta m into c square, that is 907.86 MeV. This is the total amount of energy that will be released during this particular beta decay of radium 226. I repeat, you please make this correction, this is not 228, this is 226 as per the problem. This is a typing error while typing the equation. So, certain information that we have used while solving this problem. First is the Avogadro hypothesis, that is 1 kilomole of any particular isotope will be having 6.0221 into 10 to the 26 number of nuclei. Then the mass of electron 5.486 into 10 to the minus 4 AMU that we have used, mass of antineutrino is 0, and 1 AMU is equal to or equivalent to 931 MeV. These are the informations that we have used here, and while the Avogadro hypothesis probably you already know from school level, this conversion between mass and energy, I am sure this one you already memorized by now, and I repeat again, the mass of the 3 subatomic isotopes, the 3 principal subatomic particle, that is proton, neutron and electron, you please try to remember at least to some degree, because that will help you only. Let us go to a second problem. Here it is mentioned that tritium is bombarded with deuterium, leading to a reaction given as per the shorthand notation that we have studied earlier. Here D refers to the deuterium. Now, we have to calculate the total energy interaction involved in this reaction. So, first we need to convert this shorthand notation to proper reaction format. What we have as the reactant? It is H3. So, that is tritium or 1H3. What we have as the principal product? It is helium 4 or 2He4. What other items are there? Deuterium is the one that is reacting with the tritium, and on the product we are having this N, which refers to nitrogen. So, accordingly this is the reaction that we are dealing with. So, corresponding mass values have already been provided to you, but mass of neutron I am not providing here, because as I have mentioned, that is something that you are expected to know. Now, we are writing from the energy point of view that we have studied just 2 slides back. So, the mass of the reactants and mass of the products, the balance we are taking here. This is the mass of the reactants, rest mass of tritium and deuterium, and this is the summation of rest mass of helium and neutron. The difference we are multiplying with c square, and correspondingly we are getting the answer. But one important point here, if you calculate all these masses, they are generally always available in terms of AMU, you are going to get this particular number, but C is something given in meter per second. So, this value in AMU you must multiply the corresponding conversion factor of 1.6605 into 10 minus 27 to get into the SI unit of kg, and then only you will be able to multiply with the velocity of light. So, finally, this much of joule is the energy that you are getting as the output. We can of course, always convert this to MeV using the corresponding conversion factor. In terms of here we have gone in terms of rest mass, but we could have also gone from the point of view of the mass defect that we have used for the previous problem. Like in this case also, if you calculate the mass defect is going to be 0.018882 and you can directly multiply this with 930 on MeV. So, you will get this answer, which is less than 0.1% deviation from the original one. So, either a approach you can choose and you are invariably expected to get the same result. These are the information that you have used while solving the velocity of light in vacuum, the mass of neutron, and the conversion between AMU and kg, that is a new thing that is coming, that is 1 AMU is equal to 1.6605 into 10 to the minus 27 kg, and finally, the mass energy equivalence as 1 MeV is equivalent to 930 on MeV. Now, while solving this numerical problem, we have assumed both the reactants, that is deuterium, tritium, to be stationary. While it is mentioned in the problem that tritium is being bombarded by deuterium, but we have not considered the kinetic energy of the reactants. So, let us modify the problem slightly. Here the tritium is bombarded with deuterium of 1 MeV energy. So, we have to solve the same problem, but here we have kinetic energy of deuterium also involved in the problem. So, same reactions we have, and we are writing the mass energy equivalence now, the equation that we have seen earlier. This is the kinetic energy plus the energy corresponding to rest mass, that is rest energy for tritium, and this is the kinetic energy plus rest energy, that is total energy for deuterium. So, these two together corresponds to the total energy content of the reactant, and coming to the right hand side, this is the total energy of helium and this is the total energy for neutron. So, we change their sides, that is we keep only the kinetic energy of the products on one side and keeping everything else on the other side. Here it is mentioned that tritium is stationary. Look at this particular term, tritium is stationary, as mentioned. So, its kinetic energy is 0, but kinetic energy of deuterium, that is given to be 1 MeV. So, we can put their numbers, rest mass all are given, it is coming to be 18.5897 MeV. If you compare with the previous problem where there was no kinetic energy associated with the reactants, you will find this is just 1 MeV larger, and that is only logical, because the rest energy part is remaining the same, but only the 1 MeV additional energy that is coming with the reactants, that is being added to the products, and hence this is going to be only 1 MeV more than the previous case. But this total amount of energy will be carried by both helium and neutron, and unless we solve the momentum conservation, we can't calculate their individual shares. We have a third problem. Let us now use the concept of neutron enrichment. Read the problem carefully. It is mentioned that a certain nuclear reactor is filled with uranium rods enriched to 20% U-235 and the remainder is U-238. So, you have to calculate the nuclear density of both the isotopes if the total density of uranium is available to you. Neutron or uranium enriched to 20% by U-235 refers to 20% of the total uranium content is U-235 and remainder is U-238. One information I have mentioned in the very first lecture or in the very first module when we introduced the concept of isotope, that natural uranium primarily comprises of uranium-238 and the contribution from uranium-235 is only about 0.7%. But by artificial means we can increase the amount of U-235 in the uranium sample, and that is precisely what is called enrichment. So, in this problem this nuclear reactor is using uranium with 20% U-235 enrichment level. So, we know that 1 kilomole of any element will have 6.02 to 1 into 1026 number of nuclei. Accordingly, number of uranium 235 nuclei should be equal to, here this F refers to the fraction or the percentage of uranium 235 in the total sample into the density into the Avogadro number divided by the molecular weight. M is this, M is the molecular weight. We need to know the molecular weight for both U 235 and 238, and if you put the numbers, this is what we are getting. Similarly, we can also calculate uranium 238 number nuclei for uranium 238. In this case, this F is 20% or 0.2, whereas for U 238 this is 0.8. So, if we at all need to calculate the effective molecular weight of the fuel that this particular nuclear reactor is dealing with, then that also can be calculated as F by m for U 235 plus F by m for U 238, inverse of that, and that is coming to about 237.4433 kg per kilomole. Here we are again using the Avogadro number and the molecular weight for U 235 and 238. These informations of course, you have to take from some data book or will be provided in the problem. But the same problem now we are modifying slightly. It is said that fuel for a reactor consists of pellets of uranium oxide. Generally in nuclear reactor, we shall be discussing later on, fuel is provided either in the form of rectangular pellets, that is blocks having rectangular cross section, or as cylindrical rods. So, and invariably that is generally some kind of compounds of uranium, some oxides or sulfides or hexafluorides of uranium. So, in this case you have uranium oxide and its density is given, and the uranium part for that uranium oxide is enriched to 20% in U 235. So, again you have to calculate the nuclear density of uranium 235 in the fuel. Effective molecular weight we can calculate as was shown in the previous slide for the uranium part. Now, uranium is having a molecular weight of 237 point something. Then what about uranium oxide? There the molecular weight of oxygen, 2 oxygen atom also need to be added, and accordingly this is coming to be the molecular weight of uranium oxide. So, out of this 269, 237 is coming from uranium. So, 0.8812 contribution is coming from the uranium in this total molecular weight. So, using this particular fraction, we can easily calculate the total number of nucleus present or nuclear density of uranium 235 present in the sample using the same formula, but you have to remember that this F is here not just 20%, rather it will be 0.2 into this particular fraction. Yes. So, accordingly we can calculate total number of uranium 235 nuclei present per unit volume of the fuel, and we can also do that same for uranium 238 if required at all. So, this is the corresponding answer after putting the values. Let us go to the last problem, problem number 4, which is a much more involved problem, which requires the concept of cross section as well. A thermal reactor is fueled with 100 tons of natural uranium. Natural uranium I mentioned just a while back contains just 0.715% uranium 235 and rest you can take as U 238. It is subjected to a beam of thermal neutron of intensity of 10 to the power 13 neutrons per centimeter square second. Corresponding capture and fission cross sections are given. This is the fission cross section, this is capture cross section. As no information are provided, we can consider other, that is scattering cross sections, to be equal to 0. If the average energy released per fission is 200 MeV, then you have to calculate the rating of the reactor in megawatt per ton and the rate of consumption of uranium 235 per day. So, here you are talking about fission interaction between the neutron beam that is coming and the uranium nucleus. So, the rate of fission can be sigma f into I into n into V, where I is the intensity of this neutron beam and n into V is the total number of uranium nucleus present in the target. So, here I is given is 10 to the power 7 neutrons per meter square second. Of course, the given information in the problem is in terms of centimeter square second, but I would always suggest please convert everything to SI units, then it will be much easier to solve. Similarly, the cross section is given in barns, and we know that one barn is 10 to the power minus 28 meter square. So, accordingly sigma f is 579 into 10 to the power minus 28 meter square. but we have to calculate this N into V, which is the total number of uranium 235 nucleus that is present in this particular reactor, where we have 100 tons of total natural uranium fuel. Now, total number of uranium nuclei we can calculate, that is N into V. In the previous problem number 3, we are basically calculating this N, which is density, nuclear density, but here we are bothered about total number of nuclei that is present. So, N into V that we have to compute. If we multiply both sides of the previous equation with V, then of course, the density gets converted to this mass, that is the total mass of the fuel that is present. Rest part is same. Here again the fraction is just 0.715%. Avogadro's number you know, and the molecular weight of uranium 235 is known. Accordingly, we are getting this as the total number of uranium 235 nuclei present in the this reactor, where you have 100 tons of fuel. So, then rate of fission, just multiplying with this N into V with I and sigma f, we are getting this as the rate of fission. Please note the unit is second inverse, that is this many number of fissions 1.0607 into 10 to the 19 number of fissions are taking place per unit second or per second. And in 1 second how much energy is released, that is 200 MeV given in the problem. So, if you multiply this with 200 MeV, then this is the total amount of energy that is getting released in mega electron volt per second, and MeV per second can be converted to joule per second or watt using the corresponding conversion factor. So, it is coming to be 339.85 megawatt. This is the total amount of energy that is being produced, or power I should say, because it is in megawatt. This is the power that we are getting from this particular reactor, but objective is to find the rating of the reactor in megawatt per ton. This 339.85 megawatt of energy we are getting from 100 tons of fuel. So, the rating of the reactor is 339.85 megawatt divided by 100 tons, or 3.3985 megawatt per ton. This is the reactor rating. And if we have to calculate the rate of consumption, now we know that in 1 second, I just repeat, in 1 second this many number of fission reaction is happening, that is in every second this many number of uranium 235 nucleus is getting consumed. Then what will be the total rate of consumption? That will be rate of fission multiplied by the time over which you would like to do this calculation into the molecular weight of uranium 235 divided by Avogadro's number. In this case, time refers to 1 day, that is here this time t is equal to, we are talking about 24 hours into 3600 seconds. So, once we put the numbers here, it is coming to be 0.3577 kg per day. That means, just spending 0.3577 kg of uranium 235 in 1 day, we are able to produce 339.8, that is about 340 megawatt of energy throughout the day. That is a huge fraction. If we do a corresponding calculation for a say conventional coal based thermal power stations, the fuel requirement will be in the order of a few tons, a few 100 tons. But of course, one thing we must consider here we are calculating only the rate of consumption for uranium 235, but that is only 0.715% of the total fuel. So, if you have to calculate the total rate of consumption of uranium during this, that should be 0.3577 divided by 0.00715. This should be the total rate of consumption of uranium to produce this energy level. The information that we have used here primarily are the Avogadro's hypothesis and the molecular weight of uranium 235 while solving this problem. So, that is it for this particular module. Just following the approach that is described in these 4 numerical problems, you can solve innumerable number of numerical exercises, which I would encourage you to do following any kind of textbooks, and you will be finding quite a few similar numerical problems in the assignment also. I hope you will be enjoying the assignments. And before I close off, I would like to mention the key points. If we summarize the key points from this module, first we have studied about the natural radioactivity phenomena, where we know that natural radioisotopes can disintegrate spontaneously following their own rate of decay and half-life, and half-life being a characteristic of every isotope. So, the rate of decay is unique to any kind of isotope, and such kind of decay leads to transmutation, that is formation of some other isotopes, and also emission of particles and or photons. But the nature of such kind of reactions, exactly which kind of reaction will take place, that depends upon several factors, particularly the atomic number, that is the number of protons present, the ratio of neutron to proton, and also the energy level of the parent nucleus. This is about the natural radioactivity, but from power generation point of view, we are more bothered about the artificial radioactivity, which can be induced to a stable nucleus by striking it with a suitably chosen particle accelerated to high speed. The particle can be alpha particle or proton or something else, but neutron is the most common choice, and the entire discussion that we had here and also we shall be having in the following modules, we will be considering neutron as the sole particle used for inducing this radioactivity. But the nature of neutron nucleus interaction also depends on primarily on two factors. One is the kinetic energy of the neutron, and other is the structure of the nucleus, which we characterize in terms of the cross sections. There are different types of interactions possible, and each of them has their own use, like the elastic and inelastic scatterings are primarily used to slow down a neutron from the first neutron level to the thermal neutron level, which we primarily use in the thermal reactors, whereas the radiative capture is very important in reactor design and neutron shielding or forming the core of a reactor. And finally, the magnitude of energy released or absorbed during a nuclear reaction can be estimated by balancing the rest energies of the reactants and products, and also if we want to know exactly how much amount of energy is being carried by each of the products, then we need to consider the conservation of linear momentum as well. So, that is the end of module 2. In the third module, we shall be taking it forward from this particular point, that is the concept of cross sections we have discussed here. In the third module, our topic is fission, where we shall be focusing on the fission cross section. We shall be seeing how cross section varies with the energies or energy level of the neutron, and how we can utilize that, say the phenomenon of moderation, how the elastic scattering can be used in a moderator. These things will be discussed in the third module. So, I am signing off here. So, have a good day.